first to speak. All right, welcome everyone. It is 2 o'clock on Thursday, April 13th, 2017, in UMC room 235. This is Conference on World Affairs panel number 3706, titled Astronomy's New Toys, part of the CWA Space Exploration Series. I'm your moderator, Joel Parker. I'm an astronomer with the Southwest Research Institute here in Boulder, Colorado. And I've had the opportunity of working with some of astronomy's new toys, both on the ground and in space, most recently with spacecraft that landed on a comet and flew past Pluto. And I'm looking forward to hearing about what new toys to play with in the upcoming years. Before I introduce the panelists, the obligatory please silence your cell phone and other technology that was probably partly driven by new toys in astronomy of the past. But don't turn them off, because you can use that cell phone or pad or what have you to send questions for the panelists. I will collect those questions and pose them to the panelists. And if you do not have such technology, we have old school technology in the form of producers. We have 2 producers here. And if you raise your hand, they will give you a piece of paper that you can write a question on. Yes, it's true. New technology, new toys. And they'll bring that up. If you are a student, please indicate that on your question as well. All right, so moving along, I would like to introduce our panelists here. Since this is Astronomy's New Toys, I took the opportunity to ask each panelist what was their favorite toy when they were a kid. So starting first with Michelle Thaler, who's an astronomer and a deputy director at NASA, science popularizer on Discovery Channel and NPR podcast. Her favorite toys, I'm not sure if this is as a kid or now, Star Wars toys, including a almost functional laser.
Oh, this is Nerds with Money. This is what I spend my money on now.
Okay.
I have the best fake lightsabers money can buy.
There you go. So just be warned when you ask questions. Next is David Grinspoon, an astrobiologist, author, and science popularizer, and musician. I believe you'll see him in Guitar Jam tomorrow. And other than a guitar, which was one of his favorite toys as a kid, he said another one was a hockey stick, which might explain why he likes climate modeling. Next, we have
inside joke there.
Next, we have Eric Lindstrom, a physical oceanographer who is the Climate Focus Area Lead in the Science Mission Directorate at NASA. He said his favorite toy was a teddy bear named Growly Bear, which he did not bring. Honorable mention, though, he said he had, as a child, a love affair with his chemistry set as well, so that probably led him to this work. And then at the end, we have Garrett Verschoor, who is a radio astronomer currently working at the Arecibo Observatory in Puerto Rico. His favorite toy was a tugboat, and he says he still loves tugboats. So this panel really represents a range of wavelength interests, distances from the Earth to other planets to the Big Bang. So I think we will have a lot of interesting discussion on astronomy's new toys, starting with Michelle Thaler.
You threatened to give us all of our first author papers, too, our first author paper.
I do have your first author papers. I'll name them as I do each one then. So Michelle's first author paper from 1995 was titled ultraviolet detection of the hot companion of Phi Persei.
There you go. A little catchy, huh? Yeah. Oh, God. You can see why I became a science communicator. I mean, scientific papers are painful to write, and they're even more painful to read because you have to couch all this stuff in this formalism. I thought I would begin by talking a little bit about how we actually decide what the next telescopes to build should be. Because it may surprise you that NASA just doesn't, somebody has a great idea, runs through the halls, and here, have $1 billion. There you go. It doesn't work that way. And we have to be very careful with spending public money. So I think I'm going to talk a little bit about specifically the astrophysics missions that are coming up with NASA. And I believe my colleague will talk a little bit more about the planetary science and then Earth science. So I'll stick to the astrophysics. At NASA, in the Science Mission Directorate, we currently run about 108 operational telescopes and satellites, science missions. And that's a lot to keep track of. And we actually commission studies every 10 years from the National Academy of Sciences. And they canvass scientists all over the world as to what the most pressing questions are in today's astronomy that we can answer. Is there a new technology coming online that we've never had before that will be able to answer fundamental questions about astronomy? Are there questions that are so compelling the entire astronomical community can agree that they're really important to think about? I mean, so the paper actually had a purpose. My specialty is massive binary stars and how they interact with each other in their atmospheres. That's very esoteric. You wouldn't fund $1 billion mission to study just that. I'd love it if you would, but you won't. So there has to be some consensus. Lots of arguments, lots of papers are written, lots of committees are held, but then there is actually an international agreement as to what the highest priorities are, and that's what NASA responds to. So some of the things that were identified in the past and continue to be our drivers are specific scientific questions. And in the last 10 years, one of those has been exoplanets, planets around other stars. And so that is one of the most compelling areas of study and has been identified as such. And I'll talk a bit about some of the missions that we use for that. Another is trying to figure out what happened at the very beginning of the universe. And there are several different ways to go at this, different methods of different things to look at. Is the universe expanding? Yes, it may be accelerating as well. We want to study that. The idea that the universe is made of mysterious forms of matter that we're not aware of yet, like dark matter. These are major goals. And, and another one is actually the search for life. Are there ways using astronomy, big telescopes, to actually look for the signs of life on some of these planets that we're finding around other stars? So kind of an interesting thing that I think is rather lovely is that NASA has no plans to ever build another large visible light telescope to launch into space. And the reason for that is we've gotten so good at building visible light telescopes on the ground. We use something called adaptive optics. The main thing about the Hubble telescope, and Hubble celebrated its 27th anniversary this year. One of the main things about Hubble was the idea that you would get above the atmosphere, and the atmosphere shimmers around and distorts the images. It's why stars twinkle. And getting above the atmosphere, you'd have a much better telescope. Hubble is mainly a visible light telescope. It sees a little bit farther red into the infrared and farther blue into the ultraviolet than our eyes do, but it's mainly visible light. And what happened is something called adaptive optics, where at ground-based telescopes, you shine a laser up on sort of along the site of your telescope, and the laser bounces off the atmosphere, and you see a shimmer up there as the laser light bounces back down. And then you use mathematical algorithms to model that shimmering laser and take that same shimmer out of your data. And in doing so, you cancel out the effect of the atmosphere. So the goal of NASA is there are certain wavelengths of light, wavelengths like far infrared light, much, much farther red, or X-ray light, wavelengths that actually do not get through our atmosphere at all. And you have to go to space to actually pick up this type of light. It does not come through. And so our goal is to address these major scientific questions and also use these techniques. So just to name a few, and this is like choosing between your children. I don't have enough time to actually name all 108 missions. We're certainly very excited by the James Webb Space Telescope. This has been billed as the follow-on to Hubble. The main difference, just like I mentioned, is that it will not be looking at visible light at all. It will be entirely in the infrared part of the spectrum. So all of the images that the James Webb Telescope will be returning would be invisible to you. So sometimes I get questions, is this what it really looks like in space? This is what I can tell you, absolutely not. Your eye is not sensitive to this light. That does not mean this light isn't real. It has different wavelengths, different colors. It tells you far more about the universe, actually, than visible light. Infrared spans a much broader part of the spectrum of light. We often compare it and say that if you had a keyboard of keys, all the different notes, visible light might be like the 3 notes around middle C, whereas infrared would be a whole 88 keys. There's far more information, far more wavelengths of light covered by this. Some of the major scientific goals are going after signs of habitability on exoplanets. We should be able to look at the atmospheres of these planets around other stars. And by the way, I always check. This morning, we were up a little bit over 4,500 planets that we've discovered around other stars. It changes almost every day. That's how often we discover new ones. And, so with the James Webb Telescope, we hope to analyze the atmospheres for signs of things like oxygen and water vapor and methane. And, specifically if you find those 3 molecules together, it's a very good possibility that there's life on that planet. So we're also launching the Transiting Exoplanet Survey Telescope, the TESS telescope, which will be actually doing a survey of nearby stars looking for exoplanets for the James Webb Telescope to follow up on. So we're launching that as well. We also are going into a very, very different domain as far as astrophysics, in the sense of gravitational waves. And these are something very, very different. A lot of you probably know there's a program called LIGO, which is funded by the National Science Foundation. It's the Laser Interferometric Gravitational Wave Observatory. And it's actually looking for waves. This is pretty amazing. Gravitational waves are caused, when anything with mass moves, it actually distorts space and time around it. And so we're looking for not light. We're not looking for photons. There's no light here. We're actually looking for waves in space and time itself. And they're incredibly hard to detect because luckily for us, they're at very, very small scales. Right now, your body is being pushed and pulled at tiny scales, smaller than an atom, smaller than a proton, as many different gravitational waves go through you right now. And the whole problem was detecting them. And about 1.5 years ago, LIGO made its first very strongly confirmed detection of gravitational waves. There was a gravitational wave that was set off by 2 giant black holes, both more than 100 times the mass of the sun. And they spiraled together and collided 1.3 billion years ago. And those waves just reached us last September. And the LIGO Observatory was finally sensitive enough to actually measure the compression of space and time. And to give you a sense of what they had to measure, LIGO is made of 2 observatories that are both composed of 2 lasers at a corner, at an angle to each other. And the idea is that as a gravity wave, as a compression of space and time comes through, that those 2 sides will distort differently, and you'll be able to detect with lasers that there's a difference in the length of those 2 lasers. And the lasers are on the order of about 2 miles long. And the amount that they compressed was 1/10 with 20 zeros after it. Okay, that's how much that length compressed. So if you take 2 kilometers and you divide it by 1 with 20 zeros, you get something that's about 100 times smaller than a proton. And they were able to detect that. And the better way to do this is to have longer lines to compress, longer lasers. Because you take whatever length you have, you compress it by that factor. NASA's next plan, to working with the European Space Agency, is to help with an observatory where those lasers are 1 million miles long. And as they compress, even by that tiny fraction, we can measure it much more easily. And we're hoping to even find evidence of the moment the Big Bang started to expand, actually as compression waves in space and time. Currently, NASA and the Europeans are flying the LISA Pathfinder, which is a mission to characterize all just the noise up there. It's flying right now, and it's characterizing all the noise that would get in the way of a detection of these gravity waves. And I'm happy to tell you the noise is very, very good. It's very quiet. We think we can do this. So, and that's opening up a whole new, not a set of eyes in this case, we're actually looking at we're actually hearing the vibration, the sound waves through space and time itself. I will note, I could talk about so many more. So if you have questions about more, you can say, and what's your next favorite or something? I can just go from there.
And I'm glad that you worked lasers into it. I imagine you thinking of LIGO as a huge lightsaber. You know.
Absolutely.
So next is David Grinspoon. His first author paper from 1987 was deuterium fractionation in the pre-solar nebula, kinetic limitations on surface catalysis. But there's an honorable mention. He gave a talk at the American Astronomical Society that year titled, "Was the Early Earth Shrouded in Impact-Generated Dust?" with some co-author named C. Sagan. I don't know. So, David.
Oh, yeah, that guy. Thank you all very much for coming this afternoon. And it feels funny to say this, but after Michelle's talk, I'm going to be talking about things much smaller scale and closer to home, which is not usually how I describe my research, because I work on missions to other planets. But compared to the gravitational wave and the far edges of the universe, our solar system is relatively small. Compared to our daily experience, it's relatively large. We've been exploring the solar system since, the first mission to leave Earth and successfully travel to another planet was Mariner 2 in 1961. Of course, there was a Mariner 1, which ended up in pieces around the Florida coast, which happened a lot with early planetary missions. It still happens occasionally, and launches are scary things for those of us in the planetary science, planetary exploration business, because it's one of those moments when everything has to go right. But we have had a lot of successes. I think of this as the exploration of the other planets as an amazing sort of moment in the evolutionary history of not just humanity, not just the biosphere, but of the entire Earth, in the sense that our whole planet came together in a process we call accretion 4.5 billion years ago, all the pieces falling from space and gathering themselves together in a planet, and various things happened, evolutionary processes started up, and now 4.5 billion years later, some little bits of that planet are launching themselves back out into the solar system and going out to the other planets with curiosity and sending signals back to their inquisitive builders on Earth. It's sort of a strange development, strange thing for a planet to do, if you think of it that way. And it is the time in our history when we've gained the ability to leave our planet and visit the neighbors, and we've learned a lot in these ensuing 60 or so years. A lot of the value of planetary exploration comes in insights we've gained about Earth and about our home planet, which I could go on and on about it, but won't for now, but it could be something we come back to. The toys, if you want to call them that. I have mixed feelings about calling these toys. I mean, in a way I like it because it is fun, and it's, I don't think we necessarily need to separate our playful from our serious side when we're exploring the universe, but I don't want to indicate that it's entirely frivolous, because that can make it seem wasteful. And in fact, I think now one can make an argument, I make it all the time, that planetary exploration is essential for human survival and for good stewardship of our home planet. So these are toys, but they're toys with a serious and important purpose. We started exploring the planets in the 60s on the coattails of Apollo. Apollo was the most well-funded, by far, thing that NASA has ever had. There was a brief moment where, John Kennedy made an inspirational speech, and the country lined up behind this goal to put a man on the moon. They didn't talk about putting a woman on the moon. I think maybe that will be our next thing we ought to try. But nonetheless, we put humans on the moon. It was a huge effort, and on the coattails of, it wasn't driven by science, of course. It was driven by Cold War competition. But on the coattails of that, the scientists got to do some nifty stuff, including the first wave of exploration of the solar system. Since then, we've never had the kind of budgets for planetary exploration that we had for a while in the 60s, when we did our first missions to Venus, our first missions to Mars, our first mission to Mercury, and the outer planets, Pioneer 10 and 11 were the first ones that launched to Jupiter and Saturn. And we've never had that kind of budget, but we've gotten much better at building planetary exploration machines, robots with instruments on much more limited budgets. So even though we don't have the kind of resources we haven't, again, since that time, we've learned to do more and more by building better and better instruments and getting smarter about how to build spacecraft. So a few important landmarks. I mentioned Mariner 2 to Venus in 1961. Our first flyby of Mars was called Mariner 4, and that was in 1964. And then we had a few flybys of Mars. And one thing we learned from those flybys ultimately was that flybys are not the best way to learn about a planet, because we were sort of fooled by our first couple of Mars flybys. You get a random little postage stamp image and set of data about one part of the planet, and then you're off in the solar system. You're not going into orbit. You don't get to see the rest of it. And our first couple Mars flybys, it turned out the places that we saw were atypical. And we got the wrong idea about Mars. The first couple places looked a lot like the moon, just old and dead and full of craters, which certain parts of Mars do, but a lot of it doesn't. Could you imagine trying to infer the history and nature of the Earth if you had one flyby and pictures of one random spot? Most likely it would be somewhere in the middle of the ocean, and you would come to some erroneous conclusions about the diversity and complexity of our planet. We did that for Mars. We were wrong, and our first orbiter of Mars was called Mariner 9. It was launched in, 1971, and it was revelatory. We learned that Mars is a much more complex place with dried up riverbeds and possible ancient oceans and giant volcanoes and all these polar caps with dramatic transformations, all these things we had missed, and lots of weather and climate changes, all these things we had missed on our first flyby. So since then, we've sort of developed this order of doing things with planets. Usually the first time we visit, it's a flyby, because that's easier to do. It takes more mass and therefore more energy and money to slow down and go into orbit, because you have to bring a big rocket with you that you're going to fire again and go into orbit. It's more complex. That means you're launching more mass also off of Earth. The cost multiplies. So we usually use flybys at first. Then there's a step we go into orbit, and you learn a lot more because you get to hang out and not only image the whole planet, but stay there for a while and see if things change, which in some places they do. And then oftentimes the next step is a lander. And our first Mars lander was Viking in 1976, and that also was revelatory in a lot of ways. Viking, of course, we photographed the surface. We did experiments in the atmosphere, the soil. But the big sort of point of Viking, and the most complex and expensive part of it, was the biological experiment to look for life on Mars. And the main thing we learned from the Mars biological experiment was that it's really hard to look for life on another planet when you don't know anything about life except for your assumptions, which in the case of Mars were probably kind of wrong. So that was, if anything, that was sort of overly ambitious. And now we're very interested in trying to understand the potential for life on Mars, but we're going about it in a different way, which involves characterizing Mars and its history much more than just going there and trying to find an organism and give it some food and see if it burps, which is basically what we were trying to do with Viking. And it was worth a try, but nothing burped. And then, it was like, oh, well, that was a lot of billions of dollars. But so that sequence of flyby, orbiter, lander, and then the next thing with Mars has been rovers. And of course, you know about all that. Once you can land, if you can actually have mobility on the surface, then you can see a lot more. And we've been able to do that with Mars. And there's some ideas about wanting to do that on other planets. On Titan, Saturn's moon, which turns out to be a really interesting place where we have had flybys, and we have had an entry probe to the surface, which landed briefly. The next thing we want to do is mobility there, but people are talking about a boat, not a rover, because there are lakes of methane. Wouldn't that be something, the first nautical navigation of another planet? And then the next thing, which we haven't actually been able to do yet, except from the moon and an asteroid, is sample return. That's the next big goal for Mars, because the idea is, yeah, we send these remote laboratories, but they're limited in their capability to take these complex instruments and squish them into tiny little boxes and send the stuff home. If we could have a sample of Mars in a terrestrial laboratory, there's so much more. So that's what we're working towards with Mars now, and eventually we'd love to have sample returns from a lot of these other places. It's funny, when I put it that way, I'm realizing as I talk, we're still in a very early stage of planetary exploration. We've had at least flybys to, depending on how you define it, to all the planets now. And we've had orbiters to a handful, but most of the planets, that's all. We've only had landers on Mars, and well, the Russians actually had some landers on Venus, which is a hard thing to do because it's so darn hot there. But most of the solar system is still unexplored by and large. We're just scratching the surface. The last thing I really want to mention, and there's a lot more to say about this, but on this theme of our toys getting much better and being able to do more with budgets, I mentioned the first flyby of another planet was Mariner 2 in 1961. It had one instrument on board. It was called a microwave radiometer, and it did return very important results. From that experiment, we learned that Venus is hot and not at all like Earth, and we understood that its climate evolution was very different from Earth, and that began a long and rich history of learning more and more about Venus, and which feeds back on our knowledge about Earth and how climate can change. The beginning of it was that spacecraft. I want to contrast that to another spacecraft, our most recent first flyby of another planet, which was the New Horizons mission, which finally made it to Pluto in July of 2015, so pretty recent. And by the way, our moderator, Joel Parker, was instrumental in that mission. So if I say anything wrong, Joel, tell me. But or don't. No. But the capabilities of that mission were just amazing. How far we've come, the quality of the instruments, the detail in the photographs of Pluto, and all these other instruments, the ultraviolet spectrometer, the infrared spectrometer, measuring the magnetic field, the interaction with the solar wind. It's a tiny spacecraft. It's smaller than this, it is smaller than this table we're sitting at. And it didn't cost very much compared to these other missions. It was well under $1 billion, the New Horizons spacecraft, which, maybe that doesn't sound cheap to you, but compared to Viking at Mars was several $billion. And it has revolutionized our knowledge once again of what planets can be like. Nobody knew. We hadn't explored a planet that far out in the solar system. We thought, well, maybe it's going to be a dead ice ball. It's not. It's active and dynamic and diverse and beautiful. But there were a lot of innovations that led to that mission being so much more capable, even on its small budget and with its small size. And I'll just tell you about one. I mentioned before that flybys we learned from Mars are not a good way to learn about planets, because you just fly by one part and you never get to see the rest. And that was true about Mars, but at least with Mars we had the sense, well, we'll go back with an orbiter soon enough. With New Horizons, because it's so far away and because we only were able to get, it was amazing to even get the budget approved and everything to be able to send a flyby, but that's all we were going to get. We don't know if we'll ever, maybe someday, but we don't know when, have an orbiter around Pluto. So we knew we were going to have this problem of just seeing one hemisphere of Pluto. So what could we do? We just have a flyby. Well, they did some amazing innovations, including one of the instruments is called this LORRI, L-O-R-R-I, the Long Range Reconnaissance Imager. So good having Joel here. And what this is, it's a tiny spacecraft with a powerful telescope on the spacecraft. So we think of, doing experiments with telescopes from the ground or sending spacecraft. This is a spacecraft with a powerful telescope. And they were able to take advantage of the fact that Pluto rotates with a 6.4 Earth days. And we knew we were only going to fly by that one hemisphere and get the amazing, huge, detailed images that you'd see. But we didn't want to miss the other hemisphere. So they put this LORRI telescope where when you're 6 days out from Pluto, which is the last time you're going to be able to see that other hemisphere that you're not going to fly by, you can see not bad with that telescope. It's more blurry than the other side, but they managed to solve that flyby problem so that the amount of data we got from New Horizons with a flyby is more like what we were able to get with orbiters on some of our early encounters. So it's not just a flyby in the sense that those early Mars ones were. So I guess the theme is more and more limited resources, but more and more powerful application of technology and ingenuity to survive, to continue our ability to get better and better data. And that's we have a lot of amazing success stories with that. I think I've used up my time. Obviously, there are new missions in the pipeline, and maybe we'll get back to that in the conversation. But it's a very exciting time in planetary exploration because this march of application of new technology to ingenious ways to do more exploration with less, that's something that's still continuing. So thank you.
Thank you, David. And I'm looking forward to the Pluto orbiter. So next we have Eric Lindstrom, and I believe his first first author paper was titled Absolute Geostrophic Velocity Determination from Historical Hydrographic Data in the Western North Atlantic.
Indeed.
So, Eric.
You didn't say the year, did you? Yeah.
Let's see, I do have the year here, actually. It was 1980. 1980.
Yeah, 1980. Actually, I think it's probably in the Journal of Physical Oceanography, and I'm often tell my peers that if you're having trouble getting to sleep at night, just pick up the Journal of Physical Oceanography. Yeah, this technical stuff can put you right down. So, the great thing about astronomy is, besides providing these window on the solar system, the galaxy, the universe, they really provide some great technology for looking back at the Earth. And we love to steal their ideas. Astronomy technology development, although it may be expensive relatively, it's pretty non-threatening to our politicians. Astronomers have the wonderful scientific advantage of only delivering good news. It's great stories, it's wonderful, and so it doesn't threaten anybody. Earth science, on the other hand, can feel threatening to some people, particularly politicians, and we really love to ride the shoulders of the astronomers on the technology development and keep our low profile so we can do as much without having to ask for it. So there are these things like interferometry's been used by astronomers, phased array antennas, telescopes, which we can turn around, as you said, to look at planets, and our planet is one. Also, astronomers are the big data pioneers. We are riding those coattails as well. And so there's a lot to be said. Some of the essential basic stuff that we look at the Earth are radar altimeters to measure land and sea levels. They were first used around Mars, not around the Earth. So, as you talked about the microwave radiometer from 1961. Earth scientists put the most sensitive radiometer that we've ever built in space in 2011 to look back at the Earth, so 50 years later. So these technologies are really the things that we depend on, LIDARs. I was going to mention some of the things that we've been doing. 25 years we've been measuring the sea surface height by satellite, and we have the satellites in the pipeline to keep measuring out for another 15 to 20 years. So we'll have a long time series of sea level and its variations. We know how fast it's rising, a few millimeters per year, because we can measure the surface of the ocean and its height to about a millimeter from 1,300 kilometers altitude in space. Every 10 days we map the whole planet. And so it's an incredible measurement. We can measure the surface salinity of the ocean from space. People say, well, how can you measure salinity from space? Well, it's that microwave radiometer. We measure the wavelength of microwaves. The wavelength's about 10 centimeters, and we measure the variations in this L-band microwave radiation from the surface. And it isn't just a radiometer. We have to have a suite of instruments to measure it. We have to put a radar scatterometer on the flight to measure the roughness of the surface, because the apparent salinity varies a lot with the roughness, so we have to correct for the roughness. We have to measure the ionosphere. There's something called Faraday rotation, so the radiation coming from the Earth gets rotated and changed, and you have to correct for that, the ionosphere. Only NASA can do this stuff, right? So, it turned out that we needed the astronomers yet again, because in order to get the salinity, we have to subtract a map, a shimmering map of the galactic background radiation off of the sea surface. So we have to have a map of all the L-band sources in the galaxy and then subtract that map off to get to how salty the ocean is. So, yeah, we're all tied together. So if anybody ever tells you they should take the Earth science out of NASA, please tell them that they're just crazy. We cannot do this stuff without the whole package. All the astronomers, all the planetary scientists, all the technologies. It's really important. Let me just leave it there. We need more time for questions.
Okay, thank you, Eric. So at the anchor position, we have Garrett, who has among the panel the first author paper from 1967. Not only is it the oldest, but it's the one with the simplest title, and I wonder if there's a connection there. The relation between optical and radio properties of quasars. Garrett Verschoor.
Actually, my earliest paper was 1963 or 4, and you wouldn't have found it, because those papers were written in days before computers. I'm going to take a slightly different tack here. There's a downside to all these new instruments, and what is that? It's cost. They're expensive, but the other downside is they're built without giving much consideration to what happens after they are built, which is, how do you fund them? And this is causing a tremendous crisis in astronomy. Most people overlook it because the crisis is about to happen, the really serious consequences. And I know this because my wife used to work at the NSF, so I have some insight into this. A very large telescope is being built, the LSST, the Large Synoptic Survey Telescope, which is a 27-foot mirror funded for construction in Chile. It's going to produce 13 terabytes of data every night. So we keep a lot of people busy for a very long time if they look at the data. The initial cost is almost $1 billion, and the astronomy budget is supposed to fund that one for about $37 million a year. But where does it come from? Because our budgets are not going up for operating anything. And NSF funds postdocs and scientists who already have careers at universities. But the crisis is epitomized by the following. The membership of the AAS is really skyrocketing because there are a lot of PhD students out there, and they have to get jobs. When I was a graduate, I got a job immediately because back in the 1960s, you went from your PhD to a permanent job. Then you ended up, more recently, you got one postdoc position, and then you looked for a permanent position. Today, the average number of astronomy PhDs have at least 2 postdocs or 3 before they can even hope to start looking for a job. Where are those jobs? Well, they don't exist. And by the time you've done 3 postdocs, you're 40 years old. That is a terrible situation to be in. But we keep putting money into the big projects and not funding them in the sense of operating them. To give you another perspective on this, what's happened in science, I'll be old-fashioned by pointing this out, but in 1962, when I was a graduate student, they were taking the 4 major journals in astronomy. I once calculated that I could read every astronomy paper in those 4 journals by spending 1 afternoon a week for a year. In terms of radio astronomy, I did read every paper that was published at that time. By 1992, it would have taken you 13.5 months full-time, 5 days a week, to read everything published in those equivalent 4 journals. And a few years ago, that was up to 2.5 years. So when I was young, I could actually read everything in astronomy, And now it is utterly impossible. So what do? Well, we produce all these little subgroups of people who no longer can even talk to each other. It's quite incredible. And the other thing that's happening because of this progress is that people are rediscovering stuff, and I speak for myself, that I found out 20, 30 years ago. So when we build these big telescopes, what do? Well, what is the NSF going to do? It's going to close down some smaller facilities. And I'm going to speak here on behalf of the Arecibo Observatory, where I have a emeritus position. The Arecibo telescope in the past year has been involved in 3 major discoveries, none of which would have been possible without that telescope. One of them concerns the discovery of the so-called fast radio burst, repeating fast radio burst. What is a fast radio burst? We have no idea. It's a mystery. These are sudden bursts of radio waves from distant galaxies we now know, and they last a fraction of a second, about 1,000th of a second. They're not pulsars, and when they were first discovered by accident, they thought, well, fast radio burst, something is blown up and it's gone. But Arecibo discovered the repeating fast radio bursts, and that enabled us to pinpoint where it is. It's in a galaxy 3 billion light years away, but we don't know why. We don't know anything about what's happening out there. So we're going to have to continue monitoring this. Arecibo also made a fantastically accurate measurement of the distance to the Pleiades, which the spacecraft that were launched to do this cannot match. We now know the distance to the Pleiades to a very, very high degree of accuracy. And the entire distance scale of the universe depends on knowing where the Pleiades are. And that requires Arecibo in the very large baseline, very long baseline mode. But without the collecting area of this huge 1,000-foot diameter dish, they couldn't have made this accurate measurement. And then there's nanograv, which is the poor man's way of detecting gravity waves, because the radio telescopes on Earth are linked together, and they observe pulsars, which are these pulsating radio sources. And they've got about a dozen of these pulsars in various directions, and they time the arrival of the pulses to extraordinary accuracy. And it requires a very large collecting area to help this along. So there's a couple of big radio telescopes involved. And the idea is that if a gravity wave hits us, or passes, essentially when it hits us, the pulsar timing will change. And they've been measuring this now for several years, and they reached the point, for those who are technical, of the 2 sigma level. They're almost at the point of detecting a gravity wave at a fraction of the cost of LIGO, but the gravity waves that they're going to detect are produced by slightly different types of objects. These will be massive black holes in galactic centers. So without those 3, without the big telescope, those 3 discoveries would not have been made. And now the NSF wants to close down Arecibo. And we're fighting that. And also Arecibo is used for tracking asteroids, but NASA pays for that. But if NSF pulls out, then NASA has told us that they're not going to fund all of it. And we don't know where that's going right now. We have funding until next March, and then it's open-ended. So this is a very strange time to be in astronomy. It's very strange for the youngsters coming up, because they're not going to get jobs. It's very hard. To give you an idea of how hard this is, we have a program called REU, Research Experience for Undergraduates. We had 7 positions funded by NASA, no, NSF, I forget which. We had 220 applicants. That's mind-boggling. Last year we only had 120 applicants. So, and all the universities are producing more and more PhDs because all these big instruments out there, but who's going to analyze all this data? And here I want to make a couple of points about big new toys. One of the big new toys, of course, is the CERN accelerator. And when they detected the Higgs particle, the papers reporting that had 2,000 authors. And somebody pointed out that nobody can even check whether the detection is real, because you can't even get at the data and which of those 2,000 authors really knew what was going on. And it's extraordinarily strange situation. And in astronomy, we have a couple of fantastic spacecraft up, well, one of them's upstairs still, WMAP and Planck. And they look at the cosmic microwave background structure, which is supposed to be the origin, show you the origin of galaxies. Well, the Planck papers typically have 200 authors. And most of my papers are still sole author, so I'm a sort of a dinosaur. But how many of those 200 authors actually know what's in those papers? And I suspect when they write them, can a junior author even have a say in what's going on? And I have discovered by accident, and I've now published 5 papers in Astrophysical Journal on this, that the Planck and WMAP people missed a foreground source of radiation. And that is a very strange situation to be in. There are all these billion-dollar spacecraft, and they may have missed something fundamental, which is a very strange. It still freaks me out thinking about it. But I'm working now using the Arecibo telescope to at least get some more data on that, just with one person observing instead of thousands. Anyway, so these great new toys are fantastic. I haven't said anything about their details, but the downside is the next time we have a 10-year panel that says, what do we do next in astronomy? They will come out with some fantastically new instruments, but they still won't confront this issue of how do we keep this under control, and unless you double or triple the astronomy budget, you're not going to be able to operate these things, or at least analyze the data. Terabyte of data a night? That's absurd. So anyway, I'm just old-fashioned maybe, but I think that this crisis is going to get far worse. Thank you.
Thank you, Garrett. Just a reminder, if you have questions, you can use the app if you are app savvy, and if not, you can raise your hand, and our producers will give you a 3x5 card to fill out, and then you can hold the card up and they will collect it. But first, I just wanted to give a chance for those on the panel to either do any follow-up comments on anything you said or you heard someone else say, or pose a question to one of your fellow panelists.
Well, I have a couple of comments. My facetious comment is, I think you're right, you should stop building big telescopes and give us the funding to build more planetary spacecraft. But all joking aside, you've identified some important problems, but I think it's conflating a couple of things. This business of building instruments, but then not having part of the plan be the resources to pay the people that are going to need to work on the data. That is a serious problem, and it's related to, but not quite the same as, this pipeline problem of jobs, which is not unique to astronomy, but it is something we have to think about. I mean, it's one thing when a field is in a rapid growth phase, and so there are going to be a lot more jobs in 20 years than there are now, and astronomy and planetary science have, over the recent decades had periods like that. But when that's not happening, then there's some funny math. If it's part of a successful career being a faculty member to mentor a whole cadre of graduate students, if each faculty member is, in a sense, giving birth to a large number or a handful even of grad students, and each of those grad students is expected to have a faculty job, then obviously, there's a sort of Malthusian paradox here, where there are obviously soon not going to be enough jobs for all those people. So that's a problem that's not unique to astronomy, but it's very, we're aware of it now in space, certainly also in planetary science, which is not quite the same thing as astronomy since we've started planetary exploration, but it's obviously related, and in some places is part of the same department. So what do you do? One thing is to maybe redefine the success of a faculty person, that maybe a quantity of students, and consider if maybe we shouldn't be training as many students. But another is to maybe give more emphasis to alternative careers, that somebody who's trained in astronomy or similar field, that it shouldn't necessarily be that if they don't get a faculty job at a big university that they're not a success. There are more and more, there is some emphasis being given to other careers for people who are scientifically trained in science policy, in science communication, obviously is an urgent need these days, and there are career tracks that are, I used to be a museum curator. There are career tracks that are different. And I'm someone who I don't work at a university. I work part-time at a research institute and part-time doing other things, and I don't consider myself a failure. So, somehow we have to change the math. We can't just keep producing more PhDs and then lamenting the fact that there are not going to be jobs for all of them.
Anyone else?
Carry on.
All right. Well, we're getting a lot of. Oh, was there someone?
Oh, I was just going to comment a little bit about the multiple authors. I think there's a cultural shift, and I know that Garrett was joking when he called himself a dinosaur, but it is true that I don't know in my peer group anybody that really publishes alone now. I mean, we all publish as massive groups of people, but there's a reason for that. If you were one of the scientists that was working on a science team, the idea is your name, you deserve to have your name on that paper. Yes, there have been papers that have had my name on it that all I ever did was read them and say, well, that sounds pretty good, no major objections, click, and I send it back in. I had minimal involvement, but I had involvement in setting up the instrument and taking the data and processing the data. That specific observation may not have had, I may not have been very much involved in that, but I was involved in the team that made that observation possible. And so to some extent, it's more interconnectedness. When you are working at CERN, there are thousands of people that made that possible. And as scientists, we're starting to put citizen scientists as authors on our paper. And to give you a sense what that is, as Garrett said, there's a lot of data. There are many, many terabytes of data that our NASA satellites return daily. And we found that in some cases, having a human eye look at them for different anomalies, for different things that are different about the data, is actually better than our best computer algorithms. Take looking for exoplanets. We have computer algorithms that go through all the data of our exoplanet missions looking for other planets around other stars. And the computer gets like 90% of the right stuff, and so the computer does the first pass. But some of the data is a little too messy, or the signal isn't quite right. And so we actually crowdsource this out to the public. You need no training. You go to a NASA website, and it's a very nice, easy, almost video game interface to help identify odd bits of the data. And we've now found over 1,000 candidates for exoplanets and confirmed more than 20 of them that were found by untrained members of the public. And those people ended up as authors on our scientific papers, even though they didn't have a degree. So there is a difference in in the definition of who belongs on a scientific paper. Members of the team, members of the public, and to some extent, I find the large author list something encouraging.
It's also seen as something humorous. There's the paper with 600 Steves got together to co-author a paper. So scientists recognize the humor in some of this as well.
I wanted to say that I'm glad to hear somebody else saying looking at the data is important. I sometimes get teased because I literally look at the data as opposed to putting it in a computer and letting it churn away. And I end up making maps and plotting them on a printer, and then physically looking at them and comparing them. In the case of WMAP and Planck, I know that they've taken the whole sky and processed the whole sky and came up with the answer. And when I look at small sections of that, and I say, how come they didn't see this? Because the reason is that nobody looked at the data in detail to make sure that the big picture was correct. So that's what I'm struggling with right now. It's very important to look at the data. But when you have so much data, how do you look at it? And if you know exactly what you're looking for, you will never find the unexpected, because your computer program will only give you what you were looking for. So things like pulsars would never have been discovered except by people looking at the data. But that was the old days. So I'm not sure how much we're missing these days, but we talk about this forever or argue about it forever.
Well, maybe there's a middle ground. I think that Michelle's identified reasons why multiple author papers are encouraging, but you've also identified this problem if there's no one person you can write to who necessarily actually can respond to questions about it. So maybe there needs to be sort of a first tier and second tier. Oftentimes it does say corresponding author for correspondence talk to this person, so hopefully that person is home. I've actually benefited from this in kind of a humorous way. I have a very minor role on one of the instruments on the Curiosity Mars rover, and I haven't really done that much for it, but I'm on this instrument because I helped write the proposal, and I've done a few things. But now all these papers are published that have a few authors listed, and then it says, and the Mars Science Laboratory science team, which is, you know, hundreds of people. But because I'm one of the people on that team, my number of citations, like in, you know, these H indexes and things, has gone really high recently because of all these Mars papers that I have nothing to do with, but and the Mars Science Laboratory science team, I'm one of those people, so.
I had one question to start off the Q&A here. And Eric, you mentioned that astronomy, you know, we're lucky because we only give good news. But that's until the day that we say an asteroid's heading towards the Earth.
Yeah.
That might be good news, too.
For who?
But perhaps that's one area that I don't think was touched upon too much, but the area of detecting and dealing with near-Earth objects. Does anyone want to address any new toys or technology related to that?
So one of the, I alluded to the fact that one of the benefits of planetary exploration is an increase in our ability to understand and protect the Earth. And there are a number of areas where that's true. Our understanding of climate change and how planets work is fundamentally now connected to what we've learned about other planets. And one of the things we've learned in the space age is how connected the history of Earth is to the rest of the solar system. And one of the most visceral, direct ways is that occasionally Earth gets hit by something big. We look at the moon, and what do you see? It's full of craters. Well, Earth has been in the same region of space throughout its whole history, too. So why isn't Earth full of holes?
It is.
Well, it turns out it is, but they're hidden because Earth has such a restless surface with geological and meteorological and biological activity. It sort of paves itself over, so you have to look a little harder to find the holes. But now we've been finding them, and most famously, the one that hit 65 million years ago and wiped out the dinosaurs and most of the other species at that time. There are other objects like that. The solar system is full of Earth-crossing asteroids and occasional comets, and if you wait long enough, another big one's going to hit. And, you know, one way of looking at what's new here on Earth about human beings, one hopeful way, is that, you know, the dinosaurs didn't have a space program. We do. So we know how to identify these objects now, and we actually know how to stop one that's going to hit the Earth. And so, yeah, I mean, talk about practical benefit of space exploration. We could avoid the next mass extinction by an impact. And in the long run, you can think of this as a big payback. You know, we're threatening a mass extinction now. We have to get over that. But once we get over that, then we have the opportunity in the longer run to prevent the next mass extinction and sort of turn things around and be protectors of Earth's biosphere. And I think that's an aspiration we can hold. And that, yes, planetary exploration and our new toys getting better to observing these things, mostly with ground-based telescopes, and the space technology that will allow us, when we have the need, to go out there and give one of these things a little nudge so that its orbit misses the Earth.
But you didn't mention the fact that in order to avoid being hit, you have to know their orbits exactly. And there's only one way to do that, and that is with the Arecibo radar. and it's NASA are committed through an act of Congress to make sure we don't get hit. And they're relying on Arecibo radar, but they're not stepping forward right now to take over NSF's role. But maybe that'll come down to some big head-on collision later on. Excuse the pun. The Arecibo telescope can tell you exactly which part of the planet you're going to get hit. And then you can go and move it sideways.
So we have a question here, student question, from a senior in high school. Question in general to the panel: what specific question do you all seek to answer in your current field in your lifetime? And I would add to that, does that require any new technology?
Can I start? The question that I want to answer is whether the small-scale structure in the cosmic microwave background is in fact real. If it's what I think it is, there's a confusion with foreground that they haven't taken into account. That is an incredibly important question to answer, because if I'm even halfway correct, then the small-scale structure in the cosmic microwave background is either non-existent or very different from what we think it is. And once you get there, then the whole of cosmology gets affected, because then you have to go back to the old question of how come we have galaxies?
As an oceanographer, I think it's going to take quite a long time, but I want to know how the ocean mixes. We haven't gotten our remote sensing down to fine enough scales to resolve all the eddies, the chaos of the circulation of the ocean. And it's important in climate models that we do resolve the mixing in the ocean. So that's a big challenge, and I think that it will set us on a course for a lot more advanced technologies to observe the Earth from space. But I don't discount all the need to get scientists to sea to measure small scales locally so that we can fill in all that's needed.
I guess the one big question that I hope to answer in my career in terms of a specific scientific question is why are Venus and Earth so different? We have these two nearby planets that are both the same size, remarkably similar. We don't know of any other pair of planets that are so similar in size. It happens to be the closest planet to us, and yet they've evolved in such incredibly, strikingly different directions, where Earth is like this, and Venus is a self-cleaning oven, completely dry, really hot, and we still aren't sure how much current geological activity there is on Venus, but we suspect, like Earth, it's still geologically alive. There are probably active volcanoes that are feeding climate cycles in the atmosphere. We think we know, but we haven't explored well enough to be sure. And the history of the planet is still very much a mystery. We believe Venus started out much more Earth-like with oceans. The oceans were lost. We don't exactly know when and how. We have some ideas, but it's a big mystery, and it relates to the question of habitability of a lot of these exoplanets. What is it that determines this boundary between planets that end up like Earth and can support the kind of life that we know, and planets that end up like Venus? There's still so much we don't know. When and how did Venus lose its oceans? Well, with current technology, there's a lot we could do to answer that. With just we just need some scratch, some resources to send entry probes and landers and figure out what the minerals are made out of, and a lot more about what the atmosphere is made out of and what clues it holds to the distant past of Venus. But there is a lot with new technology that's on the drawing board but not yet developed. If we could have a long-term surface lander on Venus that would survive for months or years, it's a hard thing to do at those temperatures, but people are designing new kinds of high-temperature electronics. Then we could put a seismic network on Venus, and the way we know how Earth works inside is by listening to it with seismic waves, just like, you know, you can see a fetus in the womb with ultrasound. That's how we do sort of ultrasound on Earth with seismic networks. If we didn't have that, we would know nothing about the structure and the motions in the inside of the Earth. Here's this planet next door. We know nothing of the structure and the motions, and so there's a lot, therefore, we don't understand about Earth. Is it arbitrary, or is it, to put our planet in context, we need to explore the planet next door. And so I think there's a lot we could do with current toys, but I'm very excited about the possibility of new toys that would allow us to do it better.
And why doesn't Venus have a magnetic field? It seems to me very important.
Which is another reason why it'd be great to do the seismic and understand what's going on with the convection in the interior. Yeah.
I guess I'll be a little bit indulgent, because I'll say actually the thing that just as a human being that I most want answered is there life outside the Earth? And I don't know if you guys were aware, there was a press conference by NASA 3 hours ago. I was sort of watching it on my cell phone because I've known about this result for a while. I wasn't able to talk about it, but now I can. But there's a moon of Saturn that we sampled the water of. It has an ocean, a liquid water ocean. And we actually sampled the water, and it is absolutely fizzing with chemical activity. It's effervescent with free hydrogen. There's organic molecules in it. Although this is not a 100% guarantee of life on the moon, we have very complex chemistry in a very friendly life environment. Temperature and salinity is about like the Atlantic Ocean. It's fizzing with chemistry. Wow. So that was the result that came out just 3 hours ago. So that's around Saturn. Yeah, I love that. Personally, as far as my research, I'm a specialist on the most massive stars in the universe, very, very massive, bright stars that blow up and produce things like black holes. And the wonderful thing is that we can take a picture of the universe for about 13.7 billion years ago. It's called the microwave background. It was referenced by Garrett. And at that time, we were nothing but hot hydrogen and a little bit of helium and a dusting of lithium thrown in. But those three atoms were the only atoms that existed: hydrogen, helium, tiny little bit of lithium. And if you look around us, we're made of lots of other things than that. I'm not a pure hydrogen gas creature. I'm made of carbon and oxygen and calcium and phosphorus and magnesium. And amazingly, all of those atoms were produced in the bellies of stars, which had to blow up over billions of years. And then those atoms ended up in planets that formed and then in your body. It's the only way the universe can make a carbon atom, is have it fused inside the heart of a star and have that star blow up. And the interesting thing is the universe didn't do this in a nice, easy rate. We know that these atoms are produced by exploding, dying stars. We can see that happening nearby. We can see a nearby star blow up, and we can see these atoms being created. However, the universe did a lot of it all at once at the very beginning, about 500 million years after the Big Bang. There was almost similar chemistry to the way there is now. The universe did a lot of it at once, and now it's just doing a little bit of atom creation. And we know almost nothing about that time where the majority of your atoms were created. And the James Webb Space Telescope will be the first instrument we have capable of actually getting a signal from the very first stars that ever turned on, from the very first stars that started to make more complex atoms out of hydrogen. And they may have been very different than the stars we see today. They might have been thousands of times the mass of the sun. They might have actually worked chemically very different because they had different chemistry. There weren't any calcium or iron or oxygen atoms yet. So, I'm hoping in my lifetime to get a ringside seat as we watch the first stars turn on and then see what happened all the way back from there.
Thank you. So, yes. There have been a series of questions by students and others that I'll kind of clump together and restate as relevant to access to space. One of the big costs of getting anything up there, whether it's a telescope, a person, or anything else, is actually launching the thing and getting it out of the gravitational well of Earth up into orbit or beyond. And so a lot of expense on these missions is simply getting it out there. And so there were questions here about what can be done technologically, what's in the near future, what new toys as far as getting to space, whether it's NASA or private industry like SpaceX or something like that.
Well, reusable rockets is a huge new thing. I mean, you think about it. Imagine if every time you drove somewhere in your car, you had to just leave it there and buy a new car for the next time you drove there. That's pretty much what it's been with sending things into space with rockets. And so you've seen these dramatic videos with SpaceX where they've done the landing on the barge. And this is really in its infancy, but if we get to and we will get to the point where we can routinely reuse rockets, and that's just, it makes sense that that's going to really reduce the cost of access to space. The other big thing is miniaturization. That that's a way that technology is really helping us out. And people are developing these CubeSats now, or which are like the size of this pitcher, or these little cubes that are this the standard framework for launching things cheaply and in a very small scale into space, and that opens up a whole realm of activity where students can design projects, and all these trends are reducing the cost of access to space and making it a lot easier for somebody without a lot of money to launch something. This
CubeSats are a new thing and really helping us with Earth science, getting a lot of small sensors in orbit. There are still physics that CubeSats don't necessarily help with. We need big antennas, and they're nice mesh antennas that unfold like flowers in space now, so we can get big things that fit in small packages, and so these technologies, antenna technologies, have been key for developments in earth science, and so I think smaller size is really the thing that's driving us. In the near term, reusable rockets will really come on a little bit later.
Yeah, the sophistication of these small satellites is just exploding right now. You'd be amazed what you can do with them. I mean, there's an Earth science mission right now that actually uses the GPS signals. I mean, there's signals from the GPS satellites. Well, they bounce off the ocean, and you can actually have this little formation flying. How many components does Cygnus have? Do you know?
It's got 8 satellites.
Yeah, so eight different small satellites, and it just uses the reflection of GPS signals to actually clock wind speeds over the ocean. And so you have this little set of satellites. They're small all together. They're not actually CubeSats. They're a little bigger, but they're really quite small. Or the thing that's so scary about the James Webb Space Telescope to me, I mean, la la la. I'm touching wood everywhere I go. It is incredibly complicated. The mirror is 7 times the size of Hubble's. It's a 21-foot mirror, and it can't fit into the rocket as one solid mirror. So it has to fold up like a transformer and unfold. And there are 213 different actuators that have to work for this thing to actually unfold properly. And yes, we're testing the hell out of it, of course. But I mean, that's risky. And you know, the idea of, if you want a giant mirror, fly it in segments that are free-flying CubeSats, free-flying small sats. You know, that's something we don't really have the technology for right now, but it's not that far away. So I think the idea of building bigger and bigger space-based instruments, we're going to be doing them in smaller components that work together. I mean, you guys remember the Super Bowl with Lady Gaga with all those drones flying around? That was damn impressive, right? I mean, formation flying is getting very good as far as the algorithms needed to control that. So I think we'll see a lot more of that.
I'm going to follow up on that with this plug about Cygnus, because the Mission Operations Center is right here in Boulder. Yep. At the institute I work at, and you know, you imagine all the big mission control, JPL, hundreds of controllers and people and everything, and we have a skeleton crew that is fewer in number than the satellites that are flying around the Earth that they're flying. And this is, again, due to the technology and computer capability to do a lot of the simplification of the work that needs to be done. So you need fewer people controlling it.
Yeah.
So you're partly responsible for this lack of jobs then.
That's true.
No, but a big shout out to LASP, who've been, having students run satellites for more than 20 years and doing a fabulous job.
Yeah, actually, I mentioned the New Horizons missions to Pluto, one of them, which also is largely built and designed right here in Boulder and partly at CU. And one of the innovations of that is an instrument called the Student Dust Counter, which was the first ever fully student-built, designed, managed, and run instrument on a planetary spacecraft, and it was done right here at the University of Colorado.
Yep. So we have time for one last question. Again, there were a few along this line. This one from a student, so I'll read this, but it represents the number of questions that come in and touches on to a point Garrett made about having human eyes on data. You know, you can make computers fancy, but still can't quite match at some level what humans do. And so the question is, I'm a computer science student who considers myself a citizen scientist. I actually look at the Keck exoplanet data looking for exoplanets.
Yep. Thank you.
What are your opinions on open sourcing more scientific data for the public to experiment with?
Yes.
Yes.
No objection here.
Yeah.
It's something that's happening a lot more, and it's partly the tools are there. You know, obviously the web and more computer processing and memory. With some of these planetary missions, there's this period of time where the data is proprietary, and it's a little bit of a touchy subject, but it sort of makes sense a little bit if you consider the people that have put years, sometimes decades of their lives into designing and flying these missions, and then right when the data first comes down, they're really busy just trying to keep the spacecraft running. So if you just put all the data out there, then, you know, it's sort of like they've been baking the cake for a decade and then somebody else gets to eat it, you know. So this notion of having a period of time where some of the data is proprietary and the science team gets first crack at it, there makes a certain amount of sense there, but it's also a growing trend to either initially or sometimes after a slight delay release the data to the masses. And along with that are a whole series of tools and projects that make it easier to involve people in the public, like the student who asked this question, in the data analysis. And it's not just something to do to be nice. As Michelle and Garrett mentioned, there are a lot of times when you need eyeballs that machines just can't do it as well. So it's a real win-win where people get to participate and help with the science, and we scientists get this army of citizens like helping us go through some of these big data sets.
So I think the Earth science model is a little bit different than planetary or astronomy about these keeping the data proprietary for a while. Earth science data is so many, has importance to a lot of people. I think in our division that it's all public, and we make our science team feed the public the cake. They don't get keep the cake to themselves and have it first. Their job is to bake the cake and then serve it, and maybe if there's some left over, they get theirs.
Yeah, I mean, shout out to the Earth scientists, right? I mean, one of the missions that NASA's involved in is the Global Precipitation Measurement Mission, and we run the big mothership of that. And there are other countries that run other satellites, and we produce an image, a census, a data package of all the precipitation everywhere on the planet every 3 hours. And that is made immediately public. I mean, that's the idea. You get this out to people that can use that data, maybe even save lives using the data. As a Hubble Space Telescope observer, one of the things I'll say is that our data is proprietary for 1 year. So you write the proposal, you get the money, you get the time on Hubble. If you don't publish your data in 1 year, anyone can publish it. Perfectly legal. And there are people that know, and I'm not kidding, there are people that know to the minute when your data is going to be public. Because if there's somebody that works on the same sort of thing you do and they really want that observation, they know when it's public, and you better have published it. So there is also kind of a rush in being a scientist and getting your data published before it does become public and is literally free for anyone to publish.
And I make a comment about radio astronomy. I study interstellar neutral hydrogen, and there's an all-sky neutral hydrogen survey from the Netherlands with a small telescope. There's now one from Bonn with a larger telescope, and soon the entire small section of sky observable from Arecibo will be online. Anybody can download those data, but the difficulty is analyzing those data is not simple. In neutral hydrogen studies of the Milky Way, we don't have a single image of the sky. We have hundreds of different velocities. So the data are fascinating, but very difficult to understand. And for a lay person to do that, I think is virtually impossible, because it's virtually impossible for the scientist anyway. The thing we've found is that the higher the resolution you use, the more complex the structures is you're looking at, which makes it even more difficult to understand what it is you're looking at, which is fascinating if you're involved, but to suddenly leap into that as an outsider is I think, far too difficult, unless there's some way we can invent to make it palatable, and none of us have really tried to do that yet for the outsider.
The citizen science, we do try. I mean, we take very specific things that people can help us identify, like these transits. You know, I mean, so citizen science was an attempt to let people without the scientific training actually help us analyze the data in sort of a video game-like interface. Mm-hmm. And then, of course, I mean, I used to work at the Infrared Processing and Analysis Center at Caltech. There are staffs of people, and these are some of the people that get the PhDs but not the faculty jobs, that are making data pipelines so that the data arrives calibrated and cleaned, mm-hmm. and you can mosaic many different images at once. So there's an army of people, you know, providing it to make it as easy as possible for other scientists or amateurs to use the data.
I need to jump in here because we have hit our time. Oh, okay. But this has been a great discussion. You've been a great audience and questions. Thank our panel very much.